So hopefully the connection issue is resolved today. It should work better. So what we'll do today is first I apologize a little bit if I'm not at the top. I'm a bit sick and groggy, so hopefully I won't affect too much the class. So today we're going to finish on space complexity. And then I'll save a little bit of time at the end to say a few things about the topic 11 assignments, maybe to anticipate some question you may have. So I'll try to talk about it a little bit more to clarify a few things. And then if we have time, I'll talk a little bit about the content of the exam next week so that you can come with questions on any topic of the course on Thursday, if you have some. Okay, so that's the plan for today. So let's start with, so hopefully you've all seen the YouTube video I posted on the first part on space complexity, basically what I wanted to cover last week in class. Do you have any question or things that need to be clarified from the video you saw? Okay, so there are a few people, so I'm guessing some maybe have internet issues or others. I'll record the session so I can give it to them in case. Well, at least I see Julia is here, so that means that some people have managed to solve the issue.
Yeah, I actually went to a friend's house because the area that like my house is in, the Wi-Fi is still out.
Oh shoot! Okay. So it's still okay. So that's might explain why we have so few people. Okay, thanks for letting me know. We'll still go ahead with the class, and I'll record it and send it to everybody afterwards, so that nobody really miss anything. Okay, so if you don't have any question on the first part on the video I posted, or the content of the book, the chapter 8 in the book, I'll go ahead. I'll just go through a few reminders that are important from the video. So in the video I talked about the definition of space complexity, basically the number of cells in Turing machine, the definition of space versus n space, right? N space. So as always, it's deterministic or non-deterministic Turing machine. And I talk also about the example of SAT and how SAT is, even though it's NP complete, it's actually only uses a linear space. And a key idea of why the even a complex and hard problem like SAT only uses very little amount of space is this fundamental idea that space is reusable, well, time is not, right? You cannot go back in time and change an option you've made, a choice you've made. Once you make a move, the move is made, and the time is not reused. The step is not reusable in time. While the space you can always erase and rewrite on it, right? So that's a fundamental difference that explains why there is kind of an asymmetry between the way complexity works for space or time. So we looked at the definition of n space, and then we asked the question: is n space, kind of the question we asked many times for the time question, or for even the computability question before? What is the difference between deterministic and non-deterministic? Are they the same? Do they define the same class of problems or languages? So we can ask the question: is space equal to n space? And we see in general that n space should be at least as big as space, right? Because it's more permissive. But through Savage theorem, we saw also that n space of f of n is included into space of f of n squared. So again, all of this is in the video, so you can always look at it. But we know also that n space is at least as big as space, right? So it's kind of this interesting idea that the non-deterministic machine is somewhere between the class of deterministic and the class of deterministic using square as much as space in general, right? So that's what the theorem tells us. Well, once we apply the theorem to a specific class of complexity, right? Whether it's linear, polynomial, or exponential, it's interesting to see what it tells us. And one of the most interesting results is that, well, for F linear, we looked at it through the angle of the linear bounded automaton, and we see that this theorem takes us back to the question of do we have space of O of n equals n space of O of n, and we don't know if a linear bounded automaton recognizes the same class of languages as its non-deterministic version. And we saw that before in topic 6, if I remember. Well, so in the video, I kind of go back to this question of linear bounded automaton, which is basically where you are here when you say it's linear space. That's what you have, a linear bounded automaton. Basically, you use the input, or a linear version of the size of the input, like 2x, 3 times as much, but not a polynomial version. So you can go back and look at it. Then we looked at f polynomial. What happens if f is polynomial? And what happens if f is polynomial is that using this theorem, you realize that well, you have O of n here, O of n here, and O of n square. But because it's polynomial, right? So polynomial is n to the power of k. Basically, at the class level of complexity, whether you say n to the power of k, n to the power of k, or n to the power of k to the power of 2, which is n to the power of 2k, you have the same level of complexity, because n to the power of k and n to the power of 2k are all polynomial. So you're basically saying that n space is between space and space, which means that f space equals space. So from this, we deduce that polynomial space, when you're in the polynomial space equals non-deterministic polynomial space. So what does this mean? That means that so that's quite an important result. That means that unlike for time, time, we don't know if p equals np. We actually think that it's rather p included in np. For included, I mean contained. For space, we know that P space equals NP space. So that, what does it mean? That means that if the class of languages that, and this is because of this theorem, because basically this theorem says that, and this is not about polynomial, it's in general. This theorem says if you use a non-deterministic Turing machine, it's not gonna take, I mean, if you try to translate a non-deterministic Turing machine into a deterministic Turing machine, at worst, you're gonna use the square as much. It's kind of a weird expression. Instead of saying twice as much, I'm saying square as much. You're going to use the square of the original space you're going to use. So a non-deterministic Turing machine is not really saving that much space. That's basically what this is saying. And if you're interested in polynomial, it's basically using the same amount of space, modulo an extra square. But at the polynomial level or at the exponential level, at these levels, an extra square is nothing, basically. It's nothing. So when we talk about space, whether you're deterministic polynomial or non-deterministic polynomial doesn't change anything. That's what we're saying, basically. So we were there. Now, what I didn't talk about in the video is exponential, right? 2 to the power of n. Well, here it's kind of the same thing, right? A fortiori, the square here is not gonna do anything if f is exponential. It has no impact, basically. It's a negligible impact. That's what we can say. So in the case of exponential, we define space of O of 2 to the power of n is by definition x space and its non-deterministic version is going to be nx space. Sorry. And of course, if we look at Savage's theorem again, we're going to have space of O 2 to the power of n is contained is n space of O to the power of n is contained in space of O 2 to the power of n to the power of 2, which is 2 to the power of 2n. And again, this is 2 to the power of n or 2 to the power of 2n. Sorry for the tiny 2 to the power of 2n is the same thing. They are both exponential. Sorry, it's not equal, it's contained. So basically, n space is between space and space when we talk about exponential complexity. So that means that x space is also equal to n x space. So the way you can interpret these two results, right? How you can read that in a more general sense, you can read it as at some point we've reached such a level of complexity, right? We've reached such a level of complexity that using a non-deterministic Turing machine is not going to do anything. And we'll see later again why we're saying that these are very, very, very high level of complexity. These are very, very, very large set of problems. To find problems that are, that are not in PSPACE is quite hard. Yeah, you need to invent really, really, really hard problem. So we'll see. I'll try to give you a sense today as we go forward of how powerful this is. I mean, in the sense that how large this is. And this is so large and so permissive that, again, once you reach this kind of level, and even more this one is just, I mean, to need an exponential amount of memory is just ridiculous. But even a polynomial amount of memory is already really, really, really large. And I'll try to, again, I'll try to give you a sense of that. But the idea of these is to say, well, it's so large that if instead of using a deterministic Turing machine, you use a non-deterministic, that means that you allow for any kind of branching at some point. And again, the branching really saves you a lot of time, but also space, because the space complexity is still going to be the maximum amount of space you will have used in one of the branches. But even using that, at some point, this is so large that using deterministic or non-deterministic Turing machine doesn't change anything in terms of the complexity. That's basically the idea here. Okay. Now, to get a sense of where does this fit into, you know, the classes that we've seen so far, P, NP, etc. Let's see, you know, let's try to build a Venn diagram, right? But we can't build a Venn diagram just like that, right? Is P space included in NP? Is NP included in P space? We need to make sense of that. So now that's what I would like us to look at, is the relationship between PNP and P space and P space. Okay. Any question on that so far? Are those clear? Don't hesitate to ask questions, please. Okay, so so the relationship between P and P, right, and P space and P space. Okay, so first thing to note is that we necessarily have P is included in P space. And it has to be so. Why? Because if you say that, and again, P, you know, P stands in general for P time. It's just because we use time more, we abbreviate with P, but P is the same thing as P time. So if an algorithm is in P, right, it means that you can solve it in polynomial time. So with a non-deterministic Turing machine. So you have your Turing machine, and you're going to go through you know, a set of steps. And this set of steps is at most of the order of n to the power of k, n being the size of the input, right? So let's say it takes, you know, n to the power of 3 for your problem, right? So you have your inputs on the tape start with n, right? And in the end, to solve the problem, you're going to use only the cube of that, n to the power of 3. So you're going to have a series of configuration here. Obviously, you're not going to be able to use on the tape, right? It's an infinite tape, right? So you have some blank, you can go on forever in using all of these blanks. But if this is the history of configurations, right? So you're going to use tool. So in this direction, so that's the memory. So you should kind of take this sequence and put it vertically, because I just switched here. Time is going to be like this, and space is going to be like this, right? So if the time you use is n to the power of 3, for instance, or any kind of n to the power of k, it is not possible that the space you use on your tape is more than that, right? Because even if at each step, right, your head starts here, even if each single tape step, for some reason, you write and you move, and you write and you move, and you write and you move, and you try to use as much space as you can. That's your goal, to use as much space as you can. You can't use more space than time. You can't. That's kind of like a universal law, right? We can't use more space than time. So that's a very, very important thing that proves that this has to be true, right? The class, everything, what this is saying, right? Saying that the class of polynomial languages is included in the class of polynomial space languages or problems is another way of saying, another way that is more simple of saying is that if a problem can be solved in polynomial time, then it can be solved in polynomial space, right? So ultimately, the reason behind that is that you cannot use more space than time. That's impossible. And that's why, in general, when we start talking about large spaces like this one, or even more this one, we talk about something very, very, very large and very, including a lot of problems. Because, again, space, as we said, space is reusable, time is not. And again, as I just said, we can't use more space than time. So that's true for a deterministic Turing machine. That's also true for a non-deterministic Turing machine, right? So the same way, NP has to be contained in NP space. Exact same reasoning. I'm just saying now, what I just said for a deterministic Turing machine is also true for a non-deterministic Turing machine. If my non-deterministic Turing machine is taking n to the power 3 time to solve the problem, it's not possible to use in one of the branches more than n to the power 3 space cells on the tape. Is that clear? Does it make sense? Okay. So we now have these two containments, right? So if I try to represent them, the Venn diagram, right? We know that we have P space, and NP space. But we said before, right? We showed that because of this theorem, the Savage theorem, we said last time in the video I posted that P space equals NP space. And I just explained to you briefly why this is the case. P space equals NP space. So if P space equals NP space, we now have necessarily the following containment, right? P is contained or equal to NP, itself contained or equal to space. Because NP is in NP space, but NP space equals space, P space, sorry. P space. Which is equal to NP space. All right, so we have actually the following diagram. P is in NP, and again, NP could be equal to P, we don't know. And this is in P space. And same thing here. We've said nothing about, so the same way that we cannot prove that there are problems in NP that are not in P, it's very hard to prove also. We cannot prove that there are problems in P space that are not in NP. All we said is that P space cannot be smaller. It has to be at least as big as NP, you know, because NP space has to be at least as big as NP, and NP space equals P space. So P space has to be at least as big as NP. That's all we said. Okay, so now we have a little bit more of an idea of how these can be, you know, bounded, right? How you can bound time with space. But we can also bound space with time. We can find a way to say, well, if you are in P space, that means that you need at least so much time. We can do the same thing the other way around. We can bound the time complexity of a Turing machine in terms of its space complexity. So I don't know if you remember when we did the LBA, we wanted to show that LBA that the class of language of LBA are decidable, right? So the class of language of LBA are the context-sensitive language. We wanted to show that context-sensitive languages are in the decidable languages. And to do that, that was topic 6. What we did, we said, well, because a linear bounded automata has only so much space it uses, right? We know it uses a linear space. We can actually write down all the possible configurations. So say that the only possible that this is the size of the tape, and you know, you can't go here and you can't go here, right? And let's say that the only possible because it's a limited tape and you're limited to the input, we don't really need the blank symbol. So let's say that the only possible tape symbol are 0 and 1. And that's gamma. That's our tape alphabet, right? So we have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 cells. So what are the possible configurations? Whatever configuration until I can reach a accept state or whatever. I mean, the only possible configuration of this tape is 2 to the power of 11, right? You can have 0, 1 here, 0, 1 here, so it's 2 times 2 times 2 times 2. Okay, so 2 to the power of 11 is a number of possible tape states, right? And the configuration also includes the Turing machine states, right? The Q, you know, Q0, Q1, Q. So you have to multiply that by the number of states, right? So say that's Q as the number of states. So you're gonna do Q times 2 to the power of n is the number of possible configurations. And to prove that you can always, an LBA in some sense can always halt, but you can at least always transform it into an LBA that can halt, is that if your LBA doesn't halt, that means doesn't accept or reject, that means it loops, right? Necessarily. If it loops, that means at some points you hit twice the same configuration. So if you have a limited number of configuration, you can just say, well, let's run the LBA for a long time until this number of time has passed. If this number of time has passed, then that means that at least one configuration has been encountered twice, because you cannot have more than this number of configurations. That means that there is at least one configuration that's been repeated. Therefore, halt. You halt and you reject, basically, because that means you loop forever. So even a looping LBA can be, basically, you can handle the looping LBA into some kind of exception where you know that you're looping, so you can reject. Okay, so we use that idea to say that given a Turing machine with finite alphabet and a space complexity, a certain space complexity, we can ask the question: what is the maximum time complexity of that machine? And this is the formula for the maximum time complexity. Now, we know that everything here uses PSPACE, so it's going to be a polynomial space, right? So that means that instead of 11, I'm going to have some kind of, so that means that everything here will, in terms of time, to make a decision, at worst, if you want to do the check, at worst, in terms of time, it's going to take something to the order of, let's say there is a constant c, right, times 2 to the power of not 11, but f of n, right, which is O of n to the power of k, right? But this is still exponential time, right? That's the time. That's the time it's going to take, right? So the time it will take here is necessarily less than an exponential time. So we know that PSPACE has to be included in exponential time. We don't need more than exponential time to solve PSPACE problem, because of this idea that I have a limited amount of space. It's a polynomial space, and for a polynomial space, if I take all the permutations, all the possible configurations, and I run through as many steps as there are possible configuration, which is an exponential number, then I know that my machine can halt and make a decision in this kind of limit, which is a very large limit. Again, exponential time is very large. Okay, so that's the idea. And you have a similar diagram in the book, figure 8.7. Now, what's interesting, as the book mentions, is that to ask the question, what do we know about the containment here, the inclusions of the states? What do we know and what do we not know, right? We don't know if P equals NP. As I said, we don't know if NP equals PSPACE, and we don't know if PSPACE equals X time, actually. So for each of those, basically what I'm saying is that we don't know if there is a language that takes exponential time, but does not take PSPACE. We don't know if there is a language that takes polynomial space but is not in NP, and we don't know if there is a language that is, or problem that is in NP and not NP. So it's kind of interesting to see that we know that there is a kind of containment. It's greater or equal, but if we don't know if it's equal or not, if it's actually greater. So we actually don't know anything about those containments for none of those. And here we should put, PSPACE equal NPSPACE to be complete. For each of those, we don't know. We don't know if it's what we know, however, and we're not going to prove it here, but it's in the book in chapter 9. There is a proof. We know that P is different then exp time. And it kind of makes sense, right? I mean, the idea that you can find a problem that is intrinsically exponential and not polynomial. And there is a proof for that, right? That this is smaller than this, right? There is clearly a step here between polynomial and exponential. You can design a problem that in the way it's designed, you have to go through an exponential number of steps, and you cannot go through a polynomial number of steps. But what we don't know is which one of those are they all actually like the diagram here, or do we have some of them that are, we don't know where the gap happens, because we know there is a gap between p and x time, but we don't know if it happens here, or if it happens here, or if it happens here, or if it happens on the 3, right? On all of them. So that's really interesting. Still a lot of open question here. But again, as we don't know where the gap happens, we develop this notion of completeness, right? We developed, as we saw, the notion of NP complete as a way of kind of identifying, problems that would be here if there is a gap, that would be more harder problems in NP. But we also define the same way, and we saw that, we'll see that today, P-space complete, etc., right? And you can define also X time complete, but we won't go there. But P-space complete is interesting, and we'll look at it a little bit. So, and same thing, for P-space complete, it's a way to define some problems that are considered as harder problem in P-space. And if P-space is not equal to NP or P, these problems would be the ones that are not in P or NP. So what is P-space completeness? It's really easy. It's the same thing as NP complete, basically. It's the same idea. There is one subtlety, though. To be P-space complete, you need 1 to be in P-space, like for NP complete. And 2, you need to you need to make sure that every A, so we're going to say that B is P-space complete. If B is in P-space and every A in P-space is polynomial time reducible to B. It's hard today. Okay, so and just like I didn't talk about that last time when we talked about NP and P, but just like NP hard, there's a little difference between NP complete and NP hard. NP hard is a NP complete problem that is not in NP. So it has a property of an NP complete problem, it's not in NP. You also have the definition of P-space hard. If you just meet condition number 2 and not condition number 1, you say that you're in P-space hard. So when you say P-space hard, you're actually not, it's not that you're not in P-space. It means that you don't care about if the problem is in P-space or not. You just know that this problem, if you solve this problem, you only a polynomial time step to solve all the other problems in P-space. Okay, all the other problems in P-space. So the same notion as NP completeness. but for p-space. It's really the same notion and the same definition. Now, there is one subtlety here is that we could have expected that because we are in space, here we said, we would say polynomial space reducible to B. Why for p-space, we define p-space complete as a problem such that if you solve it, you're only polynomial time away to solve all the other problems in it. One not polynomial space away. Well, it's for a very simple reason, is that polynomial time is really ultimately, it's this, right? It's really ultimately this one kind of little step. It's one, polynomial time is, in general, easy, right? It's what we consider as easy. It's doable. It's what is doable. So you want to be polynomial time away. If you're, you know, if on top of your problem that you've solved, that is p-space complete, you have to add an exponential time to solve another problem, there is no interest in that. And so the problem is that if you said, well, it's polynomial space reducible to B, that is really not interesting. Polynomial space is huge. Polynomial space is a very, very large set that includes, actually includes some exponential time problems, some very, very hard problems. So polynomial space is not what we're looking for. Again, because as I showed, when you polynomial space, you use, I mean, you can potentially have an exponential problem, an exponential time problem. So our criteria to really make basically say, well, it's only a baby step away once you solve the problem to solve all the other problems, right? So once you solve this problem, this specific problem, you've solved all the other problems. You don't want to have to add a big step. You have to add a very little step. And what we define in complexity as a little step, really, in a sense, it is the polynomial time step. That's nothing. Polynomial time is negligible. That's what we consider. I mean, it's actually not nothing, but we consider it in nature being a negligible step. Okay, so I hope that makes sense. Any question so far? Okay, so now, as usual, when we define p-space completeness, we have to find our typical perfect archetype p-space complete problem. Our NP-complete problem was SAT, right? So we're going to look here for something that is analogous to SAT. So SAT is NP-complete. And here it's called TQBF is p-space complete. And again, p-space complete or NP-space complete means the same thing because we saw that p-space equals NP-space, okay? So we want to find this kind of archetypical problem that is going to be called TQBF, totally quantified Boolean formula. TQBF is our archetypical hard p-space problem. It's actually p-space hard, right? Because everything that is p-space complete is also p-space hard, because p-space hard just consider what you need to have between p-space hard and p-space complete is to prove that the problem is also itself in p-space, which is the case for TQBF. So TQBF is p-space complete. And basically TQBF, totally quantified Boolean formula, is a generalization of the SAT problem, unsurprisingly. Why? Because again, we want to be able to code any other algorithm that would solve any problem in this very large space as a Turing machine that can be then transformed into a Boolean formula. So we still use a Boolean formula just like for the SAT problem, except that for the SAT problem, the Boolean formula had the you remember it has a form x1 or x2, and not x2 or x3. And you have to solve this problem. And when you solve this problem, you basically solve any problem in NP. That was the idea. Well, here the formula now for so that was the satisfiability problem for TQBF. Because it's a totally quantified formula, that means that all the variables here that were before free variables. So the same way that a variable is free in lambda calculus, or can also say they are free in predicate calculus or propositional logic. That means that they can take any value, right? They are not bounded by a lambda or a quantifier. Here, you want to make sure it's totally quantified. It means there's no more free variable. They are all bound to a quantifier. So it's going to look like this. There exists an x1 such that for all x2, there exists an x3, and then the formula. And this is true or false. This is true or false. Well, this is basically undefined until you assign values to x1 and x2, and you have to figure what is the assignment that works. Here, there is no assignment to make. There is no assignment because you're just already bounding them to a certain quantifier, whether existential or universal. So the question is there an x1 such that whatever x2 is, there is also an x3 that makes this work? And the answer is yes. Actually, it's x2 is whatever. This doesn't do anything because x2 cannot be true or false because of this. So yes, there is an x1 and x3 that makes this work. X1 has to be true and x3 has to be true. So this is true. Now, if I change this, there is an x2 such that for all x1, there is an x3 that makes this true. Not sure that that's true this time, because if you say, well, x2 actually, x2, whatever you decide, doesn't change anything. But so there is no x2 that makes this true, because for all x1, to say that for all x1 there is an x3 that makes this true, well, if you take x1 equals false, well, I guess if you make x1 false and x2 true, that works. So if you make this false and true, you're going to have true, false, and then you need to pick x3 true again. So this is also satisfiable, but in some cases it could be not satisfiable if you had yeah, anyway. I'm not going to get into too much of the details of these formulas. They can be really, really complicated to go through, but you get the idea of the quantifiers here, right? Because each variable here is bounded to a quantifier, this formula is necessarily true or false, right? Is there an x2 such that, and they are always the way we define them. So you could technically have the quantifiers inside the formula. This is what we call the pre-next normal form, where we put all the quantifiers in front. And so we have always the quantifiers in front, and they are always kind of alternating like that with existential, universal, existential. They are kind of hard to wrap your head around because as you add quantifiers like that, there is an x2 so that for all x1 there is an x3. It's really it's really hard to wrap your head around that. But here is a little example actually of of um, um, a case where if you invert quantifiers, you get two different answers. For instance, for all x, there is a y such that y is greater than x. That's true, right? For all x, you can always find a y that is greater, right? In natural numbers, that's true. But if now you say there is a y such that for all x, y is greater than x, that's not true anymore, right? There's no number that is greater than all numbers. Okay, so this is true and this is false in the natural number domain. Okay, so again, a totally quantified Boolean formula is true or false. The question is to figure out if it is true or false, and that's the problem. So you don't have to go through this assignment of 1 and 2. I mean, of x1, x2, x3, etc. You don't have to go through all these assignments, but in some sense, you also do. And the way you can see that is by looking at formula game. And I'll go back to that, to how it works. But the formula games show you that you can see this solving this formula as a kind of game where each player take a certain quantifier, either the existential or universal, and they all pick the existential has to make the formula be true. It has to find the one x, right? There is an x, at least one. That's going to make it true. And the universal has to find a counterexample. So in the end, it boils down to that, is to try different versions where you can make it true or false. So you can see actually solving this problem as a game between two players. One, the existential, who try to show that to make it true, and one who tries to find a counterexample to make it false. I'll go back to that. But first, there is this interesting proof to show that TQBF is p-space complete. So again, when we say p-space complete, we mean that one, it is in p-space, and two, every other problem in p-space is polynomial time reducible to this problem. I'm not going to go through the detail of the proof because it's kind of heavy and it's a bit arid, but still it's quite interesting to get the gist of it. So we can't do the same trick as we did for the proof with SAT. So we still kind of assume this table as we saw before, with all this sequence of configurations. For a Turing machine that solves, a Turing machine that solves, that decides a problem A. So it reaches at some point some kind of like Q accept or Q reject. So we have the same idea. The problem is that we use here, we know that we use polynomial space, right? Because we're in p-space. We take a problem in p-space. So here we have n to the power of k, polynomial space. Now the problem is that here we potentially have an exponential space because we have no guarantee that the problem is in NP. Again, remember we could potentially be here outside of polynomiality in terms of time. In terms of time, we potentially are outside of the polynomial realm. So we can take an exponential. So if we try to translate that into, you remember our formula phi that says, here are the conditions for all the cells, here are the transitions that are possible, etc. If we try to translate that, we have 2 to the power of n translation to make. So it's going to be an exponential time. F is going to be exponential. And that's not good because we want polynomial time reducible, right? Polynomial time reducible. So that doesn't work. We cannot just take this huge table and transform it into a formula, because then the transformation itself, although this would work in the sense that this formula would be, it would be a TQBF, it would work. It's just the transformation function is not polynomial. Okay, so the trick we use here is that we divide the table, we divide this table in half. And we say, we consider the question of going from C1, C start, to the middle, and then the middle to C end, right? The configuration that accepts or rejects. And we're going to define a certain formula phi C start, C end, T, by saying this is the formula that goes from C start to C end in maximum T steps. And for convenience, we assume that T is a power of 2. So then this formula can be described now in terms of doing the first half and the second half. We can say, well, it's this formula is, there is an M1, call it M1, such that we have phi C start M1 in T half of the steps, and phi M1 C end half of the steps. Now the problem with that is that you can then unfold, and you do, again, half here, half here, half here, half here, and you recursively define each of these by doing, well, there is a M2 such that you could go from C start to M2 and M2 to M1, etc. Problem if you do that is that this one and this one are going to themselves multiply into two formulas. This is also exponential. So you're going to reach, again, an exponential formula. So here the trick is to use the universal quantifier to instead say, and that's where we use all the power of the totally quantified Boolean formulas that we use existential and universal quantifier. We're going to say, instead, we're going to say, and I'm sorry, because this is really a really brutal demonstration, and I'm not showing all the details, but instead of this formula, we're going to say there is a M1 such that for all C3, C3, 4 belongs to, and we're going to generalize the N here by just saying, well, C3, C4 can be either C start M1 or M1 C end. So it's only on two different options. Sorry about the mess here. There is an M1 so that whether you take these two or these two, phi C3, C4 t half, half of t holds, such that this formula holds. So here what is interesting is that we now have only one formula. So we won't have kind of this exponential explosion that we had before where both formulas will become two formulas, etc. We have only one, and only this is going to get larger and larger as it grows. And this is actually this formula, this encoding of the Turing machine here. We're using the universal index exponential quantifier. We kind of guarantee that as we grow and as we divide our table by 2 by 2 by 2 by 2 until we reach an elementary stage where we just go from one configuration to the next one, which we can clearly define in a linear formula very easily, right? Until we reach the most simple ones. We keep doing this dividing, and as the formula grows to define all of that, it grows only polynomially, only linearly. It doesn't grow. Why? Because we use these quantifiers to limit, to avoid having this explosion. We just say, it's basically, we use the power of being able to say, hey, that's available, that's true for all cases. I don't need to express all the cases. I'm just saying it's true for all cases. So the introduction of the quantifiers make this problem very powerful. And then because of this power, we can now solve any problem in PSPACE. So the final, without going to the details, the final complexity of this F this time, if I use this kind of shape of formula, is going to be it's going to be n square. So it's polynomial. And why is it n square? It's because each level of the recursion here adds a portion of the formula, and this part that is always linear, so it's O of f of n, O of n. And then the number of levels of the recursion is log of this, right? The number of times you need to divide by 2 is log of 2 of n, which is basically n. So you have n, the order of n for the size, and then you have the log for the number of division, where you multiply by n again, so n times n is going to be n squared. Okay, so I'm going to pass on that because again, it's incredibly messy demonstration. If you want to look at it, it's page 340, 341 in the book. But I just wanted to give you the idea of why TQBF is PSPACE complete. And again, having a notion of how these quantified formula work is really important outside of this class, I would say. Okay, so we're almost at the end. I would say just one more word on PSPACE and games, and party board games, and where you have again, as I said, you can see the question of solving this formula as a game where you say, well, if we take this more simple one, right? For all x, there is a y such that y is greater than x. You can see the person here who has basically takes all the universal quantifier. His role is to find a counterexample, to find an x such that's not true. So he says, well, I don't think 1 million works. Okay, I'm going to pick x equals 1 million. And then the other player is going to say, well, what about 1 million and 1? 1 million and 1 is greater than 1 million, so I won. Yeah, the existential war. And actually in this game, the existential guy has a winning strategy. You can always pick this plus 1 and he's going to win. So it's always going to be true. So because he has a winning strategy, this formula is true. Now, in this game here, now we can say this player has to make it true. So he's going to pick a number y. He's going to say, well, I'm going to pick, 100. There is a y such that for all x, y is greater than x. And this guy is going to say, well, I'm going to pick 101, and I'm going to make you fail. So here now, in this turn, the universal guy has now a winning strategy. So that means this is always false. So you can see how determining if the formula is true or false is also equivalent to determining does the universal player or the existential player, right? It's a two-player game, has a winning strategy, right? If the existential player has a winning strategy, it's true. If the universal player has a winning strategy, it's false. So PSPACE, in some sense, is really kind of the complexity of games in general. You can see how a lot of games like chess or can be shown to be basically PSPACE hard or PSPACE complete. It's more like PSPACE hard because some of them are not in PSPACE. They're actually in larger classes, but they are at least PSPACE hard, right? So that means that they are in this kind of area where they are too hard to be in NP. They are exponential problems. So again, you can look in the book. This won't be specifically in this kind of question directly in the exam, but I thought it was interesting to mention how PSPACE is kind of the level of complexity of the most complex games like chess or Go or checkers, right? So what does it say? PSPACE is kind of, you can see it as a limit of polynomiality, right? There's nothing after that border that is polynomial. Everything is exponential, time, space, everything, right? So here you kind of the limit of what is computable and doable concretely in the decidable problems. So to say that chess is PSPACE hard, that basically means that if you were able to lay out in a table all the possible combinations, then you could find the best strategy and the best play in a polynomial time. But of course, the problem is that you can't lay down all the possibilities in a table because it's just too large, right? So anyway, okay, so that's the end on space complexity. Any question on that?
Will that be on the test?
Sorry?
Will that be on the test?
Well, not like specific question like the proof I just know. When I show you like the ideas of proofs like that, it's really not. It's not so that you can redo it, but it's really to try to give you more of a sense of what we're talking about and what this kind of problem can do. But no, I mean, you have to be able to define what PSPACE completeness is, right? So, but that's easy, right? We've shown that that's what PSPACE completeness is. You have to be able to give an example of a PSPACE complete problem. The totally quantified Boolean formula is an example, but you don't have to be able to even describe, even in English, the idea of the proof that the TQBF problem is PSPACE complete. Does it help? Does it make sense?
Yeah.
Now that the proof can give you a deeper understanding of what PSPACE completeness is and also NP completeness is, because the proofs are similar, that I think that can give you a deeper understanding. Well, as you talk about the test, so for the exam, the final exam next week, and I'll send an email with all of that.
It's in 2 weeks, right?
Sorry?
It's in 2 weeks?
Isn't next week Thanksgiving week?
Yeah.
So I think isn't, let me check.
We don't have any classes next week.
I thought, yeah, there's no class next week. I thought the classes next week were replaced by the exam.
That's the week after Thanksgiving.
Oh,
So,
it's
like,
the week after Thanksgiving. Oh, so
yeah.
there's kind of a break next week.
Yeah.
Oh, okay. Thank you for precision. Okay, yes. So, okay, so that's good. Good for you. More time. So I'll send you all the details, and I'll put it again as the introduction to the exam on the day of the exam. But basically, the exam will have some exercise type questions, 20 questions like that. You know, in average, they are about 2 points each. They are really the typical like exercise at the end of each chapter of the book, or like the first part of the midterm exam. So this typical like easy, quick question. You know, what is you know, give the what is the first configuration of this Turing machine or whatever. And then you have 10, so that would be about 20 exercise type questions like that. 10 knowledge type questions, which are more like multiple choice or short written response questions. Also, you know, in average 2 points each. So these ones you have to, you know, you have to give more of a, so it's either multiple choice or you have to give a response, written response, but it's not going to be like an exercise type. It's more about knowledge. And for general understanding questions are 10 points each. So these questions, the general understanding questions, they will ask more you to explain about what you learned. You know, like it will be something like, why do you think we studied finite automata in this course? What is the point of studying finite automata in complexity in computing theory course? So it's kind of a more deep understanding of how does this topic plays a role in computing theory, and what is the interest of this topic. And part of the question will be, what did you find interesting in this topic? And explain why. So it's this is going to be more of a, you know, 2-3 paragraphs question. That's why it's worth 10 points, where you really explain, you really show a deeper understanding of the topic, rather than being able to, you know, reduce a lambda expression, right? So I want you to be able to be, I want you to be tested on the, you know, the exercise type thing, like reduce a lambda expression, and also on the more like high level things. Explain what this topic brings for this course, and why it is an important topic. So it shows that you have a more in-depth understanding of the topic. So yeah, that's basically for the midterm.
And you said you were going to curve the midterm? Is that what you said?
Sorry?
Did you say you were going to apply a curve to the midterm?
No, I didn't say that. So I'm a bit groggy and tired, so I'm not expressing myself very well. No, I just described the kind of questions they will be. So 20 exercise type, 10 knowledge type, and 4 general understanding question.
Okay.
Okay. Okay, and then for the topic 11 assignments, I don't have more time now because it's already 12:15, but I'll spend a bit of time on Thursday. We're getting close to the deadline. If the deadline is too hard and you want to finish the next week, that's possible. But I would prefer not, so that you can focus on practicing on the final exam. So I would really advise that you finish this week. Topic 11 assignment, you have a lot of things are given in the content of the in Word class. You can take it or not take it. I know some people have trouble with the UI, for instance, the assignment view thing. That should not be a hindrance. Basically, the point is to give you a little bit of a head start by giving you this kind of codes that are pre-made, so that you can focus on the important things. The important thing is really to be able to define a CNF as a collection of clauses that are themselves a collection of literals. And so that's the class hierarchy thing. And then on the other side, you need to, what you need to be able to do is to ingest as an input a one-line text file that contains the CNF, and then test, and then propose the user, and that's where this little like kind of GUI window with assignments come up. The user can propose an assignment of true and false for the variables x1, x2, etc. And then you say if it satisfies or not with this assignment. And then the second step is to say, does it to find an actual solution. So if the users doesn't find one, you have to find one. So you have to test different options. You know what? I'm going to send you a little YouTube video where I explain all that, and that's going to be better than doing it, like rushing it right now. So so really 12:17. I'll see you on Thursday, and I'll send you that by email. Come on Thursday with questions you have, okay, for the course, for the final. So any kind of topic that you didn't understand, or you're struggling with, or an exercise that we've done and you're not able to redo it, or you're struggling, you come on Thursday with it, and we'll try to do this little practice session, okay? Okay, I'll see you on Thursday.
Professor, can you just stay on real quick? I just have a question about the programming.
Yes, go ahead.
Okay, so with the CNF, like, syntax, I'm just gonna type one in the chat. I just wanted to know, like, this was valid. So, like, like that, is that considered a valid clause if there's like another set of parentheses like inside, or would that
there is no point of putting parentheses inside, because because in a clause you only have disjunctions, right? You only have ors, right?
Right.
So you have,
you would never have to need the parentheses then. So
even if you have, like, the parentheses are useless here.
Okay, yeah.
No point.
When I was like parsing the text file, that I wouldn't come into one when there would be like inside parentheses.
No, and that's the advantage of this, is that really a CNF is really a set. It's just a set of clauses, and a clause is really a set of literals. And that's all you need to have. So you can really see them as basically array lists. It's very convenient.
Right. And so then, so for the CNF to be like a satisfiable, just each clause has to return like a true, like
they
Boolean.
all have to return true. Yes.
Okay, and that would be the only like thing that I would have to check for, is that each.
You only have to check does each return true, and for each clause you have to check does one return true.
Okay. Yeah. No, that sounds good. Thank you.
You're welcome. Goodbye.
Bye.